I'm Jeff Romer. I'm from the Carbon project. So this talk is about how we can do definition checking of Variadic functions. And definition checking just means type checking a definition, such as the definition of a function or a class. And that's as opposed to what C++ does with generic code, which is to type check each instantiation separately. So this talk is about our design for doing that in the Carbon language. So to start with, I'm going to give some background about what Carbon is and how definition checking works in Carbon. Then I'll cover the syntax and the runtime semantics of how we write Variadic code in Carbon. And then I'll cover how we can extend Carbon's definition checking to cover Variadic code. And then there will be a deeper dive into type checking Variadic function calls, which turns out to be the most challenging case. So first of all, how many of you are familiar with Carbon? Okay, most of you. Some of this will probably be familiar. So Carbon's an experimental successor language for C++. And successor language means that it has the same kind of relationship to C++ that TypeScript does to JavaScript, or that Kotlin does to Java. It's a new language, not an extension or a superset of C++. And instead, it targets high-fidelity interoperability with C++ and migration from C++. And that lets us explore design changes that are hard to do incrementally. And as an experiment, it's trying to answer questions like, can we build a C++ successor that meets our goals? And can it reach a critical mass of interest in the C++ community and in the industry? If you're interested in more about our successor language strategy, Chandler Carruth did a keynote about that here last year, and I'll have a link to that at the end of the talk. There's a lot I could say about the design of Carbon, but in the interest of time, I'm just going to focus on what we need to understand Variadics. I should add that all of what I'm about to show is a work in progress. Carbon is an experiment, and it's still at a very early stage, so a lot of things about it will probably change before we reach 1.0. And the proposal for the Variadics design I'm going to present is still pending, so it's even more subject to change than the rest of the language. But most of what I'll describe today is pretty well settled, and I expect the proposal to land soon. So here's an example of a function definition in Carbon. This is the function signature. The fun keyword introduces a function declaration. Then there's the name, the parameter list, and the trailing return type. This is a binding pattern, which is basically like a variable declaration. It consists of a name followed by a colon and then the type. So this function has a single parameter with type i32. And i32 is the 32-bit integer type. We also have i8, i64, and so on. And you'll also see f32 and f64, which are the 32 and 64-bit floating point types. This function returns a tuple. Carbon has native support for tuples. This is a constant definition. It starts with let, and then we have a binding pattern and an initializer. This as at the end of the initializer is an explicit type conversion. So this is converting the results of this call, which is some floating point type, to i32. And this is a variable definition, which is pretty much the same as let, but it's introduced with var. And hopefully the rest of this looks pretty familiar. Here's an example of a call to that function. And this line is roughly the Carbon equivalent of a C++ structured binding. And it's actually an example of Carbon's general support for pattern matching. Instead of a binding pattern after the let, like in the previous example, here we have a tuple pattern. A tuple pattern is roughly the same syntax as a tuple literal. It's parentheses with a comma-separated list of elements. But the elements are patterns rather than expressions. So instead of constructing a tuple from the elements, this is destructuring a tuple into its elements. As I said before, these are called binding patterns. And a binding pattern basically has two roles. First, it's a declaration. It declares a variable with a particular type in the current scope. And second, it's a pattern. It matches a value that's convertible to that type, and as a side effect, it initializes the variable with the converted value.
question.
Yes.
Are the types necessary there?
Yes, they are. There can also be auto, but you need the colon and then something in that position.
Okay.
So as a whole, this, sorry, yes, another question.
Yeah, so when you call a function like this, do the return values travel through a fixed layout tuple type? Or does the language actually take the pattern and merge it into the called function and directly initialize the separate variables of factor and has factor?
I don't think we've really determined that yet. Chandler, do you?
The return type is a tuple type, and so smallest vector has to initialize a tuple. But we can actually just bind names to the members of that tuple, so it's not like there's going to be a copy. But there has to be a tuple structure because smallest vector initializes it in that memory layout with the current design.
So that means that you do have to pack and unpack things like tuples and expecteds and all that stuff. You can't do what you do with input parameters, which is just the compiler decides where they live in registers or on the stack somewhere in completely separate places, and we just initialize them.
All we can do, but
Yeah. Yeah.
I hope this doesn't derail too much, but just like the on the binding pattern, it's got to be it's some sort of valid name. Like there's some restrictions on variable name. Don't start with like weird characters, and then the types have to be a type that's already existing at that point in the program.
Yes, that's right.
Okay, and then also the other one is if I want, well, let's keep going on. There's plenty of other things.
Okay, so yeah, as a whole, this pattern matches a tuple whose first element is I32, second element is convertible to bool, and binds the names factor and has factor to those converted elements. You might have noticed this tuple pattern has the same syntax as a function parameter list, and that's not an accident. A function parameter list in Carbon is a tuple pattern. And similarly, the argument list of a function call is a tuple literal. So the first step of a function call is matching the argument tuple against the parameter pattern. And by the way, throughout this talk, I'm going to be using the word parameters to refer to the patterns in a function signature and arguments to refer to the values that are passed by the caller. So one of the key features that distinguishes Carbon from C++ is its generic system. So here's a very simple example of a generic function. This is an implicit parameter list. It's a list of parameters that are deduced rather than being passed explicitly by the caller. And in this case, there's only one parameter. This is a binding pattern, but the exclamation point makes it a compile time binding, which means the bound value has to be fixed at compile time. And the type of this binding, core.add, is actually a constraint that says that T is a type that supports the plus operator. I'm not going to talk about how constraints are defined. If you're interested, there was a whole talk about it, about Carbon's generic system here last year that's on YouTube. So T is a parameter whose value is a type. In Carbon, types are values. So you'll sometimes hear me refer to things like the value of T, even though T is a type. Now, suppose I added this print statement here. So this wouldn't actually compile because it contains a type error. T might not be printable. Unlike in C++, it's a type error even if we only ever call generic sum with types that do implement printable. And in fact, it's a type error even if we never call generic sum at all. That's because this function is definition checked, which means that it's fully type checked when it's defined, just like an ordinary function. So if we want to make this code compile, we could add a printable constraint to T, or we could make T a template binding by adding the template keyword. And that makes T behave basically like a C++ template parameter. It means the function will be instantiated separately for each argument type that it's called with, and the code that depends on T, which is basically the whole function, won't be type checked until that instantiation. As a result, the constraint core.add now acts like a C++ concept. It constrains what types you can call this function with, but it no longer constrains what you can do with T in the function body. Question?
So I just, you said earlier, and I just want to make sure I got the words because the vocabulary could be important. T is a parameter.
I'm colloquially referring to it as a parameter. Yeah,
Okay.
This syntax is a binding pattern.
Okay, and yeah, the binding pattern, that would be the parameter.
Yeah, I'm just
So-
a binding pattern in a function signature is typically referred to as a parameter.
Okay, thank you.
Yeah.
So without the template keyword, is generic sum just implemented once as a routine that can be called? Because you said that with the template keyword, it gets instantiated once with every possible type.
Right. Without the template keyword, like on the back end, the code might be generated for this multiple times, like in C++. But as far as the type checker is concerned, there's no instantiation. This is just type checked once and we're done. Whereas here, this gets instantiated for each different t during type checking, and then each instantiation is type checked separately. Does that make sense?
So without the template keyword, it wouldn't get instantiated?
Not during type checking.
Okay.
It just type checks this essentially as if it were a normal function body.
It's like early type checking versus late
Yes.
type checking.
Yes, exactly. So one of the main use cases for having both kinds of generic bindings is migration. That part of being a successor language is that it has to be easy to migrate from C++ to Carbon. And template generics let you migrate your C++ templates to Carbon without having to give them fully precise type constraints first. And then if you want, you can go back and try to add those constraints and turn it into a non-template parameter.
Sorry, one
Yes.
last thing. If we had two, like if we had a T and a U, like if we only added template to T, but constrained U to be core addable, do we still check use usage?
To the extent we can, I believe so, yes. The idea is we can't check anything that's dependent on a template binding, but anything that's not dependent, we can check immediately, and we do.
All right. And so if anything's a template, then it's all late checked. But
Right.
yeah. All right.
And you should be able to do all that even if your callers are still in C++, because the interop layer should be able to expose this in C++ as a template. So those are some of the key ideas behind Carbon generics. What I'm going to be talking about today is how we can extend that approach to cover Variadics. A Variadic function is basically a function that has a generic arity. In other words, it's generic with respect to the number of arguments, not just with respect to their types. So when we're looking at adding Variadics to Carbon, our main goal is to make sure that the benefits of Carbon generics also apply to functions that have generic arity. In particular, we want them to support definition checking, and we want to provide that incremental migration path from C++. We also have a couple goals that are more specific to Variadics. We want a programming model that emphasizes iteration rather than recursion. That avoids some performance problems that I'll explain in a little bit. And it's also easier to reason about because most people find iteration easier to reason about than recursion. There are also some other smaller pain points of C++ Variadics that we want to address while we're at it. In particular, we want to support homogeneous Variadic functions. That's functions that take some number of arguments of the same type. And we want to allow Variadic parameters to go at the beginning of the parameter list, or even in the middle, not just at the end. Thank you. Finally, something that's more of a constraint than a goal, we want type checking to be efficient. Carbon prioritizes rapid development cycles. We think we can make Carbon several times faster to compile than C++, and we don't want Variadics to jeopardize that. Ideally, compile time should be linear in the size of the inputs. And we don't, in particular, we don't want the compiler doing things like searching in a multidimensional solution space. And type checking especially shouldn't require that because it's fundamentally about verifying types that should mostly already be expressed in the code. So I'll start with the syntax and semantics of Variadic code, what it looks like and what it does at runtime, and then we'll get into how we can actually type check that code. So here's a simple example of a Variadic function in Carbon that just returns the sum of its arguments. This parameter list says that int sum takes an arbitrary number of arguments that all have type I64 and binds the name param to those arguments. And param is a pack, which is a sequence of values, a lot like a tuple. The elements of a pack can have different types, but in this case they don't. I'm going to circle back and explain how this signature works in a minute, but it's actually easier to start with the function body. So the ellipsis marks the beginning of a pack expansion. And a pack expansion is a kind of compile time loop. And there are several kinds of pack expansion, depending on the context where they appear. This one occurs in a statement context, so it's a pack expansion statement. It consists of an ellipsis followed by a statement called the body. A pack expansion statement iterates over a pack and executes the body once for each value in the pack. So in this case, it's iterating over param. In other words, this is basically a compile time range-based for loop. The body of the expansion is the body of the loop, and there's no loop header because the body implicitly specifies what we're iterating over. Was there a question?
I'm just trying to figure, like, each word there probably has some significance.
Yes. So it's called an each name. And it consists of the keyword each followed by the name of a pack. And it can only occur inside a pack expansion. And it behaves like an iterator over the pack. So on the nth iteration of this pack expansion loop, it refers to the nth element of the pack. So you can think of an each name as the name of the nth element of the pack for an unspecified n, or for an n that's specified by the surrounding context. And this is the only way to refer to a pack. You implicitly refer to a pack as a whole by referring to its elements.
Okay, so you need the sigil every time.
Yes.
Okay.
Sure, I think.
I need to formulate my question.
Okay, sure, go ahead.
So if you need the sigil every time, why have the sigil?
So this is borrowed from Swift, by the way. The advantage of it is that it makes it locally explicit what the expansion's iterating over.
Right.
So we think that helps readability. It also means the compiler can always tell when we're referring to a pack, even if the name is non-local. And that solves some problems for things like member packs, for example. It also, this is sort of a side benefit, but it avoids a style dilemma that we have in C++, which is, do you give this thing a singular name or a plural name? Because a singular name tends to feel awkward in the parameter list, but a plural name tends to feel awkward at the point of use. With each, a singular name usually feels fairly natural in both places.
Do you have pack indexing?
Not yet. We potentially could in the future. So there may be, we may relax the rule that you can't refer to a pack without each, but right now that's the.
I mean, that's what each is gonna say for you, right? Because the ... indexing syntax in C++ is yes. But this is the equivalent of this one is template 4, right?
Roughly, although it's sometimes useful that this doesn't introduce a scope. So you could, for example, have a variable declaration in this statement. And that would declare like a pack
if you
of
didn't put a
variables.
compound statement in there, right?
Sorry, what?
If you didn't put a compound statement in there.
Right.
Right.
So two
Yeah.
questions. One of them is, I assume that within that sort of, if I wanted to use each param twice, say to maybe add them both together, I could do that by just like each param plus each param, and it would be essentially referencing it twice.
Yes, exactly.
And then you mentioned that you can't use it without the ... sequence. There's no way to, are you able to then pass parameter as an argument to another function? So sort of taking that param pack and just like pushing it down to others?
Um,
Or do you have to unroll it first, roll it up again, and pass it down?
You have to basically unpack it into a parameter list. Yeah. Yeah.
Would you ever use each param in the function body without preceding the statement with dot, dot, dot?
No, it can only occur inside a pack expansion.
And would you ever use param inside of the function definition without preceding param by each?
At present, no.
And could we do a nested pack expansion here?
No, we don't support nesting yet. We'd like to. We left it out of the initial version mostly to keep things simple.
Yeah, but it would probably look kind of like each param plus parens dot 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 each param.
Yeah, I mean there's some subtleties about like inside the nested expansion, like which of the two loops is controlling the iteration of the each name. So there are some problems to solve there.
Yeah, it would be nice to get both both Cartesian products and lockstep expansion, which are both a mess in C++. So
yeah. So yeah, as a whole, this statement loops over the elements of param and adds each of them to sum. Here's an example of a call to int sum. When a pack expansion occurs in an expression context like this one, it's a pack expansion expression. And it can only occur inside a tuple literal. It consists of an ellipsis followed by the body, but the body is an expression. And it's a compile time loop like a pack expansion statement. But since the loop body is an expression rather than a statement, each iteration produces a value. And then all of those values become elements of the enclosing tuple. Here we're iterating over two packs, or rather two usages of the same pack. So we're iterating over them simultaneously in lockstep. Yeah.
I'm assuming you can put extra arguments before and after by just putting value, comma, then the pack thing, comma, then something else.
Yes. Yes, before or after the ellipsis. So yeah, this line of code is calling int sum once with an argument list that consists of the square of each element of param. So now that we've covered pack expansion statements and expressions, we're ready to go back and talk about how the signature works. It starts with an ellipsis, so it's a pack expansion. But remember, the parameter list of a function is a tuple pattern. So this is a pattern context rather than a statement or expression context. And that makes this a pack expansion pattern. A pack expansion pattern can only occur inside a tuple pattern. So it's always matching elements of a tuple, such as the arguments of a function call. It consists of an ellipsis followed by the body. This time the body is a pattern. So it's a compile time loop like the other kinds of pack expansion. But because the body is a pattern, rather than repeatedly executing a statement or repeatedly evaluating an expression, we're repeatedly matching a pattern. Specifically, we're matching the body pattern against a sequence of tuple elements. In this case, the arguments passed by the caller. Here, the body is a binding pattern, which consists of a name and a type. In this case, the name is an each name. Like I said earlier, a binding pattern has two roles. It's a declaration and a pattern. As a declaration, this binding pattern declares this name with this type. And an each name refers to the nth element of a pack for some unspecified n. So this is literally declaring each element of param with type I64. And that means it's implicitly declaring the pack param itself. So this is the flip side of what I said before, that you don't refer to a pack directly, you refer to its elements. And as a pattern, a binding pattern matches any value that's convertible to the declared type and initializes the named variable with the converted value. Since this name is an each name, on the nth iteration, this initializes the nth element of the pack. So in a sense, the each name is behaving like an output iterator instead of an input iterator in this context. If this wasn't an each name, we'd be trying to initialize the same variable on each iteration, so that's disallowed. Inside a pack expansion pattern, all binding patterns have to have each names. Yes?
Do you have something like a underscore in C++ that just matches something without introducing a value?
Yes, yes.
And so you could just say ... underscore I64, and this matches arbitrary I64s without giving the values?
Yes, although you would need to make it each underscore, I think. We probably haven't specified that explicitly.
Okay.
So putting all that together, this pack expansion pattern matches an arbitrary number of arguments that are all convertible to I64, declares a pack named param whose elements are all I64s, and initializes the elements with the converted argument values. So in other words, param is a pack of all the arguments. As a result, this behaves a lot like a C++ parameter pack declaration. But in C++, you'd need to make the parameter types be template parameters and then constrain them to be convertible to I64, because C++ doesn't support homogeneous function parameter packs. This is one of the minor pain points that we wanted to address. So here's a more realistic example. Stircat concatenates its string-like arguments into a single output string. And string-like is a hypothetical interface that has toString and length methods. And the length is important because it lets us reserve space for the output up front instead of having to reallocate as the output grows. Here we have a pack expansion pattern that's mostly like before, but the type is a little different. Here I've added some parentheses to show the structure of the syntax. This is a pack expansion pattern, so it consists of an ellipsis and a body pattern. It works in a loop, matching the body pattern against each argument passed by the caller. This is the body pattern. It's a binding pattern, so it consists of a name and a colon and a type, declares the name as having that type, and matches a value convertible to that type and binds the name to it. This is the name that's being declared. Incidentally, it's not valid syntax to put parentheses around the name part of a binding pattern, so that's why they're grayed out here. This is an each name, so it behaves like an iterator. On the first iteration, it refers to the first element of param, and so on. But here we're declaring each param and implicitly declaring param, so it behaves like an output iterator. And this is the type of the bound value. In this case, the type is an each name, so it behaves like an iterator over T. On the first iteration of the pack expansion, it refers to the first element of T. On the second iteration, it refers to the second element, and so on. And notice this is a usage of each T, not a declaration of each T, because it's not followed by a colon. So putting those together, we're declaring an element of param, and we're saying that its type is given by an element of T. And since pack expansions iterate simultaneously, as a declaration, this binding pattern is saying that the type of each element of param is the corresponding element of T. And as a pattern, this binding pattern is matching a value that's convertible to each T and initializes the name with the converted value. And pack expansion patterns iterate over a sequence of tuple elements to match, which in this case is the sequence of arguments. So this binding pattern requires that each argument is convertible to the corresponding element of T and initializes each element of param with the corresponding converted argument.
I probably forgot to ask this earlier, which would be relevant here. What if I wanted to have two constraints, string length and loggable, or something like that? I didn't actually ask that earlier. Can you provide multiple constraints to an argument?
Yes, there's an and operator that does conjunction of constraints.
And you would specify that where the string like word was. You'd say, hey, the constraints are here. You wouldn't say there's one constraint, comma, another constraint. It's more like, here's my constraint with more.
Right. You'd say like each t colon bang string like and other constraint. But yeah, so each t is a deduced parameter. So when we say that an argument type must be convertible to an element of t, that means we're deducing that element of t to be the type of that argument. And then we have to check that the type that we deduced satisfies the constraint type string like. And then over the course of the loop, we build up the full contents of t. Question?
I assume that this would need pack indexing, but there's no way to say pick the first t and have that be the return type instead of a fixed string.
That's correct. You'd need pack indexing. This signature is saying that strcat takes an arbitrary number of arguments, which must all have types that implement string-like, and it binds param to those arguments and t to their types. These two statement pack expansions work pretty much like the one that I showed before, but one interesting thing to notice is each always applies directly to the name of a pack. So in these two cases, we're calling a method on each param. We're not applying each to the result of the method call. Each really is part of the name. You can also think of each as an operator with infinitely high precedence. So overall, the function body uses a pack expansion statement to compute the length of the concatenated outputs, reserve space for it, and then uses another expansion statement to append each input to it. For comparison, here's an example of how something like strcat is often written in C++. And I particularly want to focus on strcat impl, which splits the parameters into first and rest, appends the first to the output, and then recurses on the rest. So if you call this with 10 arguments, you instantiate strcat impl with 10 parameters, and then you instantiate it again with 9 parameters, and then again with 8 parameters, and so on. So compiling this takes quadratic time. It could even be quadratic at runtime because it needs to pass a quadratic number of parameters.
Is there any reason you can't implement this with like pack expansions in C++?
So you can. It's possible to avoid that quadratic overhead with something like this. This is basically equivalent to the Carbon version. It's using a fold over the comma operator to get the same behavior as a pack expansion statement. And this is a cool technique, but the problem with it is that it's a cool technique. When people teach C++ Variadics, they always start with the recursive version, and then this sort of thing is an advanced topic if it's covered at all. And that makes sense because the language kind of steers you away from it in a bunch of small ways. It uses the comma operator, which we're often taught to avoid, and it can subtly break if somebody overloads the comma operator. You need to put these funny like top-level parentheses around it. It only works with expressions, so if you want to loop over a block of multiple statements, you need to factor it out as a function or a lambda. And overall, it just kind of feels like an accident, not something the language actually wants you to do. Question?
Or maybe even a comment or observation. I think what you're maybe getting to is, like by having, if you went to the previous slide, by having this ability with templates to say, okay, you have a parameter, you have a template pack, but you can also sort of say, you can also pull the front off that parameter pack. It leads naturally to doing recursive things. And then like the language lends itself to that, and you're like, oh, I should follow that paradigm, and then you end up in quadratic sort of expansion situations. And with your strategy with Carbon, you're like, oh, you know what, you don't really, or do you have the ability to do this sort of thing of like take the head off and get the rest of a pack? Like, or is that one of these, no, we restrict that so we prevent recursion from even occurring?
You can do this kind of thing in Carbon. I think the more important difference is that Carbon has pack expansion statements as a first-class language feature that we can teach when we're first introducing Variadics, so that you never need to go to recursion in the first place. And so yeah, our hypothesis is that by having this, we can make recursive variadics much rarer in practice.
Right. Give them the ability to fall into the pit of success. As
Exactly.
opposed to, it's harder to figure out the right thing to do.
It's sure a lot shorter than template 4.
Yeah.
But maybe there's a meta statement here about how if there was an easier way to express it in a language, it can ensure success.
Yeah, definitely. And yeah, I think it would be really great if C++ had template 4 or even something more Variadic specific like this.
I'm just looking for the status of the template 4 paper.
The most recent status I know of is that the author abandoned it. I don't know why. I don't know if anybody's planning to revive it. But it's possible there have been updates since then. So here's min, which returns the minimum of its arguments. And there are a couple interesting things to notice here. In this case, t is not a pack because it's not declared with each. So we have to deduce a single type from all of the arguments. The current rule in that situation is that all of those deductions have to deduce identical types. So that you need to call this function with arguments that have identical types. We could do something like say that we deduce t to be the common type of all the argument types or something like that. But the problem is that we can't guarantee that common type is associative. So the result could depend on the argument order and the evaluation order. So it's still kind of an open question whether we can do better than that.
Wait, sorry.
Yes.
I was writing another. Orderable means specifically what?
So ordered, it just means that supports less than comparison.
Thank you.
I don't think that's actually what we call this interface. This is just an illustration.
Okay, so I just checked the status. They need a new revision to just codify the decisions that EWG has made, and it's going directly to core.
Oh, okay, cool. So another thing to notice is this function takes a singular parameter as well as a pack of parameters. In general, a tuple pattern can contain singular patterns as well as a pack expansion pattern. But it can't have more than one pack expansion pattern. In this case, the pack expansion is at the end of the parameter list, but that's not required. It could also go at the beginning, or it could even have singular patterns on both sides. This is another of those C++ pain points that I mentioned before. Yes?
I also missed this. You said that t has to be the same type, not the same constraint, but the same type?
Yes, so t is a type, and it's not marked with each, so it's not a pack of types, it's a type.
Okay.
So yeah, we have to deduce
Everything has to be
a single value for it.
I see.
So when you have a mix of singular patterns and pack expansion patterns, the way that works is that the leading and trailing singular patterns match first, and then the pack pattern in the middle matches whatever's left over. So this signature splits the argument list into the first argument and the rest of them. But this isn't recursive like stircat impl was. The body is still iterative. We're splitting the parameter list like this in order to require that there's at least one argument, because it doesn't make sense to take the minimum of no values.
Oh,
yes.
Can the ellipses match on no arguments, or is it
Yes.
have to be?
Yes, a pack can be empty. So here's just some examples of calls to min. The first call doesn't type check because a pack can be empty. Each x might be empty, in which case there wouldn't be anything for first to bind to. So that first call doesn't type check. But the rest of the calls are okay because the compiler can see that there's going to be at least one argument. But the shape of the argument list doesn't have to match the shape of the parameter list. And that's important for consistency with C++, and because the caller shouldn't need to care about whether first is at the beginning or the end. It's essentially an implementation detail. And then, as you can see on the last line, a tuple expression can have multiple pack expansions, even though a tuple pattern can't.
So, is there a way to assert to the compiler that the pack has at least one element?
At present, no, except by using the sort of the first next trick.
Because we do that a lot with a requires expression, and so.
Okay. Yeah, that was.
Yeah.
Yeah, we actually we spent a while trying to find a syntax like that so that you wouldn't have to use this first next trick and could just state it more directly, but we couldn't come up with a syntax that was satisfactory.
Can you create packs inside a function, just like the structured bindings can introduce a pack kind of thing, so that you can concatenate a first and each
Yes.
in a pack, and then you have a pack that's everything, and you can do everything uniformly?
Yes, because yes, a parameter list is just a tuple pattern. So pretty much anything that you can do in a function call, you can do in the function body with a pattern match with a let or var.
Okay.
So if you had a parameter pack, I want to make sure you use the right term. So if you have that the pack and it has 3 elements, but I sort of did that binding to 4 elements in the ... Would that just be a compiler error? Like, which is, hey, you're trying to overexpand something that's not there. Meaning, if I can say through the let syntax that I'm pulling the first element out and the rest is the pack, pull the second element, what happens when you exceed the number of elements that are in the pack?
So you'll get a type error.
Okay. Yeah. So, that would be a type error.
Yeah. And yeah, we'll get into that a lot more shortly. So yeah, summing up, we have basically 2 new syntaxes here to support Variadics. An each name, which refers to the nth element of a pack, which is how you declare a pack and how you use one. And a pack expansion, which is an ellipsis followed by a body, and is basically a compile time loop, where the body is the code that's getting executed on each iteration. The body can be an expression, a pattern, or a statement, depending on the context. An expression expansion is a loop like std transform. The body maps inputs to outputs, and the inputs are each names in the body, and the outputs are tuple elements. A statement expansion is like std for each or a range-based for loop. The body just gets executed on each input. And the inputs are each names in the body, and there are no outputs except side effects. And then a pattern expansion is a pattern matching loop. The inputs are tuple elements being matched, and the outputs are pack elements declared in the body. Yeah, go ahead.
Yeah, my question is like, how does the compiler know like which like packs to iterate on inside the body? Like, would it be a really complicated block of code inside the like an if statement or something that's distributed with 3 dots? Yeah, how does that work?
It iterates over all of the each names in the body simultaneously.
So if there's 2, like if you have 2 packs inside the same body, would that break everything or no?
Nope, it iterates simultaneously over both packs.
If they have different lengths?
They can't have different lengths, and there's another constraint that I'll get to when I cover type checking.
Okay, cool.
Yeah.
What was that? Statement expansion or statement expansions. Is there a restriction on like does it need to be one statement or are there techniques you like? Okay, well I'll move a whole bunch of statements into a lambda, but I sort of like captured that each parameter and just had like an expression that way.
I mean, it needs to be a single statement, but we're going to have some kind of block statement.
Right.
So you know,
some block that very easy to see.
So yeah, I mean, just like a for loop, essentially, you'll be able to have a block as the body if you want to execute multiple statements. Yeah.
For the statement expansion, is there any restrictions on what kind of statements can you have? Like, can you have like a variable definition there?
Yep. Yeah, I can't think of any restrictions. It is binding patterns inside a pack expansion have to have each names so that you're not initializing the same variable multiple times. But I can't think of any restrictions on the kind of statement.
So I can have something like ... let, I don't know, let each copy equals like param, and that just makes a new pack.
Yes.
With copies of the param.
Yeah.
Oh, so you can introduce packs by doing ... var each name.
Yes.
That is cool.
And can these appear in like struct bodies as well, or does it have to be in a function body?
I think you'd need to use a lambda or something to put a statement inside a struct body.
So like you can't use that directly implement like something like a std tuple then.
Yeah. So there is sort of a missing piece here that we don't have pack expansion declarations yet.
Okay.
Which we would need for something like member packs. That is something we'd like to add, though. Any other questions about the syntax and semantics before we move on to type checking? Okay. So yeah, that's how we write Variadic code in Carbon. But our goal here isn't just to be able to write it and run it; it's to be able to type check it. So that's what the rest of the talk is going to cover. I'm going to start with how we type check within a single pack expansion. And then in the next section, I'll talk about how we type check function calls, which is really about how we type check the interaction between pack expansions. So before we can really talk about checking the types in Variadic code, we need to figure out how to represent those types. So we'll start with this toy example. We need to figure out how to represent the type of X. It's a pack, so its type is going to be some sequence of element types, like a tuple. But what's the actual sequence of element types here? We know the first element is going to be I32. We know the last element is going to be F32. But what goes in the middle? It's going to be some number of repetitions of I64. And specifically, that number is going to be equal to the number of elements in param. Here I'm using vertical bars as the usual math notation for the size of a sequence. In C++, this would be easier because we don't type check until the function is instantiated for a given call site. And then we would know what the arity of param is, and we could write I64 that many times. But our goal here is to definition check the function body. So we're type checking as soon as we see the body rather than type checking each instantiation. And for a homogeneous function like this, we shouldn't need to instantiate it for each call site anyway, even at code generation time. We should be able to generate code once with a calling convention that passes the arguments as an array. So when we're type checking, we don't know the arity of param, but we need to represent a type like this anyway. And this is how we do that. This notation inside angle brackets is called a segment. It consists of an expression and an arity. And a segment basically means evaluate this expression this many times and make a sequence of the results. In other words, it's a kind of loop that evaluates an expression and produces pack elements. And that makes it a lot like a pack expansion expression, but we're specifying the number of repetitions explicitly. So it's sort of like a traditional for loop rather than a range-based for loop. And this lets us represent repetition generically because the arity can be an expression like it is here instead of a concrete number.
Sorry,
yes.
Unrelated, but a let binding just gives new names to existing things. It doesn't change type or copies or anything.
A let binding can cause implicit conversions, but it doesn't copy unless The conversion might happen, which amounts to a copy, but the let itself doesn't cause a copy. So yeah, if the types match, then there's no copying. So yeah, this is how we write the type of each x of x. For consistency, I've written the first and last elements as segments with length 1, so that the pack type consists entirely of segments. However, this isn't Carbon syntax. It's just a notation that we use for talking about the type system math. You can't actually write out a pack type or a pack value or a segment in Carbon code, or use the vertical bars to take the size of a pack. And that's because we've designed the syntax and semantics so that you rarely, if ever, need to. The first design that I came up with actually had syntax for those things, and it was awful. For example, you'd have to declare param with a pack type and say that it has n repetitions of I64, and then you'd have to declare n as a deduced parameter of f. And it was all very principled and very explicit, but it was incredibly noisy and complicated. So we decided to make segments implicit and propagate arities by deduction instead of making you write them out explicitly. And then that makes the syntax much cleaner and more readable, but the price is that we have this sort of dark matter hidden in the type system. So these segments are all some number of repetitions of exactly the same value, but that's not always the case. Here I've made param heterogeneous, so different elements can have different types. But in order to do that, I've introduced a name for those types, which is t. So if we wanted to write the contents of this pack type with expressions rather than segments, we could do that pretty easily using a pack expansion expression. But for consistency, we want to always represent packs as sequences of segments. But remember, a segment is basically a pack expansion expression with an explicit arity. So we can turn this into a segment by making the arity explicit and using angle brackets instead of an ellipsis. When a segment contains an each name like this one, we say that it's heterogeneous. Otherwise, we say it's homogeneous. So that's how we represent pack types. We also need to take a closer look at tuple types. For example, we need a way to represent the type of this tuple. And normally we'd represent a tuple type with a list of element types, but we can't do that here for the same reason we couldn't do it with the pack type. This tuple has the same element types as x. The only difference is it's a tuple of them instead of a pack of them. And so we represent it, it's the same information, so we represent it in the same way as a sequence of segments. At least in Variadic contexts, a tuple type is a sequence of segments rather than a sequence of elements. And outside of a Variadic context, they're just all segments of length 1, so we can just refer to them as elements. So that's how we represent Variadic types. Now we'll look at how we use them in type checking. I've switched back to the homogeneous version of this function to keep things concrete. So let's start by trying to type check this expression. So remember, a pack expansion is a loop, so we're going to evaluate this expression multiple times over the course of this statement. And it's going to have different types on different iterations. On the first iteration, the type of this expression is going to be I32. On the last iteration, it's going to be F32. And on all the other iterations, it's going to be I64. So instead of a singular type, this expression has a sequence of types. We can't write out that sequence explicitly because we don't know how many repetitions there will be, but we can represent it as a sequence of segments. In other words, we can express the type of this expression as a pack. In this case, it happens to be the same as the type of x. In general, inside a pack expansion, the type of an expression or a pattern is going to be a pack of types. We do need to be a little careful here, though. Normally, when we say an expression has a type, that means that you can evaluate that expression and produce a value of that type. But that's not the case here. This pack expansion is going to execute this whole statement in a loop. So we evaluate this expression once, pass the result to print, evaluate it again, pass the result of that to print, and so on. So the different values of this expression don't even have overlapping lifetimes. We could imagine sort of vectorizing that loop, at least in simple cases like this, so that you evaluate this expression once and get a pack of values. But that doesn't really work if the expression contains things like branches. So we do need to stick with the fundamental model that this is a loop. So this expression has a pack type, but not a pack value, just a sequence of values over time. So here's a more complex example. We're multiplying elements of two different packs. So let's try to type check that. Pack expansion is a loop, so we can figure out the pack type by figuring out the type on each iteration. On the first iteration, the two operands have types I32 and F64. And when you multiply those, the result type is F64. We can't figure out the type on the second iteration in particular because there might not be a second iteration. These packs, because param might be empty. But we do know that all the iterations after the number of iterations after the first one will be equal to the arity of param. And we know that in all those iterations, it'll be the product of two I64s, which is an I64. So the type pack has two segments, a singular segment with type F64 and a variadic segment with the same arity as param and type I64. And this generalizes. A pack expansion is a loop, so we can type check it in a loop, but it's a loop over segments, not a loop over elements. And as a result, we have to require that all the packs in an expansion have the same shape, meaning that corresponding segments have the same arities. So for type checking pack expansions, the key idea is to represent packs and tuples as sequences of segments rather than sequences of elements. And that's valuable because it lets us represent things like repetition and arity explicitly but generically. And we can then use that when we're type checking inside a pack expansion by saying that every expression and pattern has a pack type. And to make that work, we require the input packs to have the same shape. Yes?
So if you went back to the last example, sorry to go back.
Yeah.
You didn't catch it. So in this example, what we've done is we said, okay, I've got I32, my first element of the x variable is going to have I32 followed by a param, a sequence. And so it's two segments. And what if the other side was now that I said instead of y being an F64, then the parameter, but instead I wrote it as parameter F32, 64. And at that point, then y would be a parameter segment and a single F64. Would it still fall out that you could do this? I think you'd be like, hey, I've got segments, but they're different. They don't match in terms of their shape.
Yes.
But you could still deduce that, yes, there's one, followed by, there's a single, followed by a pack and a single. Could you type check that sort of?
So that would be disallowed. We do something like that for function calls, which I'll get to in a minute.
Oh, okay.
But within a single pack expansion, everything has to have the same shape.
Well, I could, if I hadn't used x and y together in that print statement, I could still have written it. Like if those two types never interact with each other.
Right. If they never appeared in the same pack expansion, that'd be fine.
Okay, thank you.
Okay. So I did gloss over something here, which is how do we type check these first two lines? On each of these lines, we have two separate pack expansions, which are connected by pattern matching operation. So the type on the left has to match the type on the right. In this case, that's pretty trivial because we used auto. But suppose I gave them concrete types. In that case, the first line is correct, but the second line shouldn't type check because F64 isn't implicitly convertible to I64. So far I've been explaining how we type check within these pack expansions and compute the types of these tuples. But in a pattern match like this, we're checking how two different expansions relate to each other.
Can you do an explicit conversion?
Yes, you could explicitly convert. But yeah, this line is written, shouldn't compile. So yeah, this is the last piece of the puzzle, is type checking pattern matching. Once we're able to type check the interaction between pack expansions in a pattern match, we'll have a complete story for type checking Variadics. But this turns out to be the most challenging part of that story. And I'm going to focus specifically on type checking function calls, because they're the most important kind of pattern matching. And in some ways, they're the hardest to type check. The good news is this isn't always hard. There's some common cases that are comparatively easy. So I'm going to start with those, and then I'll talk about how we can reduce many of the harder cases to an easy case. So here's a very simple example of a Variadic function call. It's easy to check because all the argument types are the same and all the parameter types are the same. So we can just check one arbitrarily chosen argument against one arbitrary parameter, and the result of that type checking will work for all of them. In terms of the segment representation, we're checking a single argument segment against a single parameter segment, and they're both homogeneous. So there are two parts we need to check, the types and the arities, and we can check them independently. To check the types, we just have to check that the argument type I32 is convertible to the parameter type I64, and it is. For the arities, we need to verify that they're equal. And that's easy because the arity of a pattern is always deduced. So in this case, we can just immediately deduce that the arity of param is equal to the arity of x. So this type checks. Did anybody spot the bug in this code? There's division by 0 because x could be empty. So here's a fixed version where I've used the same trick as with min, splitting the parameters into first and next to make sure that there's at least one of them. But now that means there's two argument segments and one parameter segment. But that's still okay. There's only one parameter segment. So clearly we need to check the first argument against I64 and then check the second argument against I64. In other words, when there's a single parameter segment, we can loop over the argument segments, checking each of them against the parameter segment. And then we just need to check that the arities are equal, which means deducing the arity of param. The general rule is that the sum of the argument arities is equal to the sum of the parameter arities. So we can immediately deduce that the arity of param is equal to the arity of next plus 1. In this example, we only have one argument segment and one parameter segment, but there. Sorry, yes?
Can you go back?
Yeah.
So the idea almost is like when you come up to a parameter, it's like sort of an infinite number. Like I add 1 to it, no problem. It's just arity it's a pack, and so it sort of works. Sorry, can you repeat what you said there? I missed it.
Basically, there's only one parameter segment here. So when we go to check each argument against the parameters, we need to figure out like which segment to check it against. But that's easy because there's only one segment that we could possibly be checking it against. So we check it against that one. We check the first argument against the type I64 because there's nothing else there that we could that it could potentially match with.
Got it. If it's a single thing that's a parameter, you just got to go through all of the segments. Go, hey, do you match? Do you match? Do you match? Great, perfect. We have no problem.
Exactly. So yeah, just like in the first example, here we can check the argument segment against the parameter segment, and then check that the arities match. These are now heterogeneous, but that doesn't make that much difference because the segment representation lets us work with a single expression that abstracts away the variation. The other difference is that now the parameter segment has a deduced type. So now we deduce each t to be each u, and then that means we need to check that each u satisfies the constraints on each t, which in this case it does. So here's a modified version of that example. We have two argument segments and one parameter segment. So we iterate over the argument segments, checking them against that parameter segment like before. And while we're doing that, we're also deducing a value for t by concatenating the segments that we check it against. So this example is sort of an alternate implementation of strcat that's implemented in terms of stir_append, which takes an output parameter. So now there are 2 argument segments and 2 parameter segments, but we know that the first argument, the first parameter is going to match the first argument and only the first argument because they're both singular. Question?
Is there a comma missing between the stir star and the ellipses on the second line? Where's that?
Yes, there is. Sorry about that.
Okay, thank you.
Yeah, not sure I missed that. So yeah, the first argument has to match the first parameter because they're both singular. By elimination, that means the second parameter has to match the second argument, and only that. So we just have to check the first pair against each other and the second pair against each other. In this example, we have 2 parameter segments and 1 argument segment. And this doesn't type check. The problem is that X could be empty, but if it is, there will be nothing for first to bind to. In terms of the segment representation, the problem comes when we try to deduce the arity of next. The sum of the argument arities is equal to the sum of the parameter arities, so we have 1 plus the arity of next is equal to the arity of X. Next is what we're trying to solve for, because the arity of a parameter is always deduced. So we get the arity of next is equal to the arity of X minus 1. But you can't subtract from the arity of a pack because it might be 0. So this isn't valid, the deduction fails, and this doesn't type check.
That's very cool.
So here's a modified version of that example, where we still have only 1 variadic argument segment, but we've built it by concatenating each X with a singular Y, so it's guaranteed to have at least 1 element. So in terms of the segment representation, the arity of the argument segment is arity of X plus 1. So the sum of the argument arities is equal to the sum of parameter arities. So we have 1 plus next equals X plus 1, which we can solve to get arity of next is equal to the arity of X. And there's no subtraction here, so we're good. We still need to check that the types match, though. But for that, we can do the same thing that we did before when we had 2 argument segments and 1 parameter segment, but we're doing it with 2 parameter segments and 1 argument segment. In other words, the first parameter has to be checked against F64 because there's nothing else that we can check it against. And the second parameter segment needs to be checked against F64 because there's nothing else. One twist in this case is that T is deduced but not variadic, so we have to deduce a single T, and we handle that by deducing T separately for each argument segment that matches it, and then check that we deduce the same type each time. So those are all comparatively easy cases, and they're easy for the same kind of reason. Either each argument has only 1 parameter that can match it, so we can just check each argument against its 1 parameter, or each parameter has only 1 argument it can match, so we can just check each parameter against its 1 argument, or both. But it doesn't always work out that way. And here's an example of that. So zip takes a bunch of vectors of values as arguments and returns a vector of tuples of those values. In this case, the author's chosen to require at least 1 argument by adding a singular parameter to the front. And the call site has at least 1 argument, but it's at the end of the argument list instead of the beginning. And that means we don't have that simple pairing off of arguments and parameters that we've had up till now. First could match the first element of X, or it could match Y if X is empty. And next will match Y, but it may also match the trailing elements of X if X has more than 1 element. But we can see that any possible instantiation of F with concrete types would type check. There are basically 3 cases we need to consider based on the arity of X. If X is empty, then first matches Y and next matches nothing, and that type checks. If X has exactly 1 element, then first will match that element and next will match Y, and that type checks. If X has 2 or more elements, then first will match the leading element of X and next will match the remaining element of X and also Y. and that type checks. So if we can figure that out, maybe the type checker can apply the same reasoning? Here's a more abstracted version of that example. The table on the right shows which arguments need to be checked against which parameters. But what happens if we add another singular argument to the end and another singular parameter to the front? Now there are 8 argument parameter pairs to type check. The only one that we can skip is that the very first parameter can't match the very last argument. And now I've added a 4th argument and parameter, and now there are 13 pairs to type check. And now there are 19. You can probably see the pattern here. The amount of type checking that we have to do is growing quadratically with the number of arguments and parameters. And remember I said earlier, one of the constraints we have is that type checking needs to be efficient. And if at all possible, it should be linear time. And this approach doesn't satisfy that. So we need to figure out a way to make this tractable. One option is to say, don't write your APIs this way. For example, we could say that you can't mix singular and variadic parameters, so this signature for zip isn't allowed unless you put next inside its own nested tuple. We've also considered a relaxed version of that, where you can mix singular and variadic parameters, but a singular parameter can only match a singular argument. So this signature for zip would be valid, but this call site wouldn't be a valid call to it. In either case, we're basically telling the caller and callee to coordinate in order to give us enough structure that the call falls into one of those easy cases. That would break plausible use cases like this one and like min. We could potentially fix that by giving them a workaround like we talked about a few minutes ago, some way of explicitly setting a minimum on the arity of a pack so that zip doesn't need to split its parameters like that. But there's a more fundamental problem with solving the problem by imposing those restrictions. Carbon's a C++ successor language. So one of our goals for Variadics is to support incremental migration anywhere in the call stack. I need to be able to turn my C++ Variadic function into a Carbon Variadic function without changing my callers or my callees. And either of those restrictions would block that because they restrict what the call site can look like. So we need to find a way to accept function calls like this. The key insight here is that we can rewrite this signature so that it only has one parameter. And that reduces the problem to one of the easy cases. Each argument has only one parameter that can match it because there's only one parameter at all. So the answer here is for the compiler to perform a rewrite like this as part of type checking. It actually does that in terms of the segment representation, not in terms of a literal code rewrite. But it's a lot easier to understand this as a rewrite, so I'm going to present it that way. But keep in mind that under the hood, this is going to be happening in terms of segments.
Right.
Question?
But then if you did that rewrite, you've lost the requirement that you need at least one.
Yes, we'll get to that. So the way the type checker can do that is it starts by noticing this entire tuple pattern consists of binding patterns, which always match so long as the types match. And the names don't really matter. The type checker can invent its own names. So these patterns both essentially match anything so long as the types work out. So that being the case, we can merge them into a single pattern that's equivalent to the original if we can merge their types. But even if we can merge their types, we need to solve the problem that you just pointed out. The original form requires at least one argument, and the rewritten form doesn't. But the compiler can fix that by internally remembering that param has to match at least one argument. There's no syntax for that, but we're not actually doing a syntactic rewrite. This is actually happening in the type system where the compiler can keep track of this. So I'm going to use this green box for the stuff that's in the type system that's not visible in the rewrite. So now we just need to merge the types. The first step is pretty easy. The original types are all vectors. So the new type is going to be some kind of vector. But a vector of what? We need to merge the element types. And the key realization here is that these names are both usages of deduced parameters. And they're deducing usages. In other words, they're the usages that actually drive the deduction. And that means that they too can essentially match anything. And so we can merge the usages of these parameters by merging the parameters themselves. And just like with explicit parameters, we can merge them if we can merge their types. So now we just need to check that we can merge the types of the deduced parameters. And merging these types is easy because they're identical. And then finally, we need to rewrite the return type because the signature doesn't have first and next in it anymore. Clearly, it's going to be a vector, but we need a rewrite for this tuple type. And we already have an equivalence for exactly that tuple type on the last line of the green box there. It tells us exactly how to rewrite it. And now we're done. Now that we've rewritten this signature, we can use it in place of the original. Most of the stuff in the green box isn't meaningful now that we're done with the rewrite, but this arity constraint is still meaningful. So we have to keep it, or the function would be callable with no arguments, unlike the original. So it becomes a hidden part of the function signature. And now that we've rewritten the signature of zip, this is one of the easy cases that we've seen before. For each argument, there's only one parameter that can match it, so we check each argument against that parameter. In this case, we've merged all the singular parameters into the Variadic parameter. In other cases, it might not be possible to merge all of them, but it might be possible to merge some of them. And if so, we do that, because the more parameters we merge, the more possible call sites we can type check. Here's a somewhat more contrived example. F is a function that negates its first arguments and then adds all the remaining arguments to it. And those arguments can all have different types, but they have constraints to make sure that those operations are supported. Here again, the singular parameter comes first in the signature, but the singular argument comes last at the call site. So we're not in one of the easy cases. This time, we can't merge the parameters because they're genuinely different. They have different types and different constraints. And first is also different from next because it's used to deduce the return type. So we can't just treat the parameters as a single parameter that's been split up. However, the arguments are all the same type, and that means we can get to an easy case by rewriting the call site to merge the arguments. Specifically, we'll try to introduce a new variable that holds all the arguments so that there can be a single argument segment. And for that to work, we need to be able to merge the types. And in this case, that's trivial because they're the same. And with that done, we're back to one of the easy cases where each parameter can only match one argument. So the details are a little different, but this is fundamentally the same thing that we did with zip, but applied to the arguments instead of the parameters. In this example, the arguments all had concrete types. We can also do this kind of merge if they're all generic types with the same constraints by doing a second layer of merging like we did with zip. So the overall process of type checking function calls is that first, when we type check the function declaration, we merge as many singular parameters as possible into the Variadic parameter. And then at the call site, we deduce the arity of the Variadic parameter. And that comes first because the arities will determine how the arguments and parameters match up. Then we check if each argument has only one parameter that can match it. If so, check each argument against its parameter and we're done. If not, we merge the arguments as much as possible and then check if each parameter has only one argument that it can match. And if so, we check each parameter against its arguments and we're done. If not, we're out of options and type checking fails. Yes?
So that part at the end where type checking fails, does that mean that it is possible that even though I've written something that through the longer attempt would work, this would fail type checking?
So yes, this algorithm isn't fully general. It's possible to construct examples that will fail under this algorithm, but that would provably always type check if they were templates. However, so far, all the examples that we've come up with are really contrived and don't seem like code that people would actually expect to work. Because this approach seems to more or less correspond to how people reason about type checking Variadic code.
Yeah, and if necessary, you still have the template escape.
Yes, exactly. Yes, you can always turn it into a template. But yeah, our hypothesis right now is that this type checking algorithm will accept the vast majority of real world code. And as the carbon experiment moves forward, we'll be looking to falsify that hypothesis with usage experience. So I'd just like to conclude by circling back to the goals that we started with. First of all, we wanted to support definition checking in variadic functions. We did that by introducing the idea of a segment, which gives us a generic way to represent things like repetition and arity, and said that packs and tuples are sequences of segments. Then we said that inside a pack expansion, expressions and patterns have pack types, and that lets us generically represent how their types change across iterations of the expansion. Our next goal was to support incremental migration from C++ anywhere in the call stack. The main challenge for that was function call type checking. We needed function calls to be structured in a certain way, but C++ API conventions don't surface that structure. But we have to be able to support those conventions, so we try to infer that structure rather than having the programmer give it to us, which we do by merging parameters and merging arguments. We can do that in linear time, which satisfies the constraint that type checking should be efficient. And our hypothesis is that it will successfully infer enough structure for real use cases. We also wanted to shift to a programming model based on iteration rather than recursion, because that has benefits for both readability and performance. The key to achieving that was pack expansion statements, because they let you write procedural loops over packs without resorting to recursion or esoteric tricks like comma folds. Pack expansion expressions and patterns are also fundamentally iterative, even if they're not loops in the procedural sense. As of now, it might still be necessary to use recursion if you want to express something like a variadic data member, but we'd like to close that gap in the future. And finally, we wanted to address a few minor pain points of C++ Variadics, and we did that. We have native support for homogeneous variadic functions, and variadic parameters can appear at the beginning or middle of the function signature, not just at the end. So if you're interested in more details, this link here has the full language design proposal that this is based on. The proposal is currently somewhat behind what I've presented today, but I'm planning to bring that up to date and land it pretty soon. The second link is to our GitHub repository. Carbon has a fully open source development model. So this is where the development of the language design and the compiler actually happens. And we welcome new contributors, and there's information in the repository about how to get started. So if this kind of work seems interesting, please come join us. Are there any questions? Thank you.
So I expected quite a few cases that that's a very typical functional programming zip, right? Because you need them to be callable with a specific signature, and that's all. Like, I don't know how you can even come up with a type annotation for that.
Well, off the top of my head, I can't say exactly what that type annotation would look like. Actually, maybe I unplugged too soon. The design for function types is in progress right now, but
the thing is, those are always overload sets.
Yeah, but that. I'm not sure that'll be an obstacle, actually. I can show you an this is not the this is not what function types will actually look like. This is just a sketch, but maybe this will help point toward how this kind of thing can work.
It's not the thing.
Okay.
That. So the problem is you get a pack of functions and you need to apply the composition.
Oh, I see. Oh, so you're applying a sequence of function calls.
Yes, and those might be wrapped in maybe, which means if you don't have a function, you just short circuit it, but otherwise you zip over.
Okay. Yeah. Huh.
And that's like that's higher order to the point that it's, you know, I don't know how to write that.
Yeah. That might need to be a template, but it's hard for me to picture a use case for that wouldn't already be a template.
Yeah. Fair. I mean, I don't even know how you would write a successive application as a pack. Or you'd have to be declaring and using the previous one. It's kind of weird.
Yeah, I'll have to think about that one. I'm not sure. Question? Yeah.
One thing I'm curious is like, does this like early checks save you time at the instantiation time, or is the instantiation type checking identical between templates and non-template generics? Like, do you save some time later by doing this earlier?
Yeah, presumably, because we're only type checking once rather than type checking for each call site.
So like an instantiation, you don't run through another type check?
If there's no templates involved, then yeah, there's no need to. Because yeah, there's nothing new to learn. Anything else? Okay.
Excellent talk.
Thanks.